You're listening to Let's Talk Creation.
Well, welcome back to another episode of Let's Talk Creation with Todd and Paul. I am Todd Wood.
And I'm Paul Garner.
And if you're new to this podcast, welcome. We're glad to have you here. If you've not seen us before, we do what the name says. We're two guys who talk about creation. So there you go. Sometimes it's theology, sometimes it's Bible, sometimes it's science, and so forth. This episode is going to be a little complicated because it's science again. So brace yourselves. We're going to try to get into the thick and the weeds here on issues of physics. So I hope you'll stick with us. We'll try to make it pretty understandable. Before we get going, though, I want to remind you, leave a like on our video if you're watching on YouTube. If you're listening on a podcast platform, do consider leaving us a review. Share our stuff far and wide. We do appreciate all that support that you give us. And every little bit helps us to continue to produce the podcast and to continue to grow our audience. So we thank you for that. All right, Paul. This is another episode. Let me just start here. This is another episode in our series on radiometric dating. So you'll recall, those of you who've been with us for a while, you'll recall that we've started this sort of intermittent series of episodes on how conventional scientists work out how old things are in our world. Mostly focusing on rocks and physical material on the planet, and occasionally stuff that comes from outer space, but mostly on the planet. Previous episode, the first in the series, that was the dripping faucet episode, where we went through this really long analogy trying to explain the basic logic behind any sort of radiometric dating process. There's a bunch of them, so we just tried to boil it down to something simple. The previous episode in the series, we talked with a scientist, Ben Clausen, who works on radiometric dating, and we asked him to explain to us, some real basic stuff about how it works. And I admit, we left that episode kind of dangling, right? We didn't give you any, clear, but wait, there's more kind of stuff. We just sort of left it with, this is how it works and this is how they use it. And that I think ruffled a few feathers. But hopefully you'll see here with this new episode that we do have a plan, a long-term plan. We're not just going to leave you dangling. So stick with us. All right. So, Paul, this episode is all about the RATE project. Can you tell me in, 30 seconds or less, what does RATE stand for and what was it all about? What was the point?
Yeah. So the RATE project was basically a team of researchers who were convened back in 1997 by the Institute for Creation Research and the Creation Research Society. And the term RATE is actually an acronym. It stands for Radioisotopes and the Age of the Earth. And basically the idea was that this group of creationist researchers would come together to look at the methodologies and results of radiometric dating methods and would survey the state of the art and then do some research of their own to try to understand radiometric dating within a creationist framework. So that's basically what the RATE project was about.
I remember the launch. I remember it was a big deal. I remember ICR was looking, the project, ICR especially, was looking to raise a lot of money. I mean, this was no small thing that they did. So how much was that they were going after?
Yeah, it was a big project, and I think they raised about $1 million or something on that order. It was
that's what I remember.
It was basically funded through private donations from people who just wanted to see this project happen.
Yeah. Yeah. So, yeah, that was, I just remember at the time sitting there thinking, this is great. This is the kind of thing that needs to happen. And I remember thinking, that's a lot of money. And I don't know how they're going to do this. Right. And I don't think they've ever really duplicated that. I mean, they've had other sorts of project, but I don't think they've ever had anything quite to the same magnitude in my recollection, because this was a long, involved process.
Yes.
Multiple years. How many years did it go? 7 years, something like that?
It was 8 years, I think. It ran from 97. I think they had their first meeting in 97, and then the final sort of rate book came out in 2005, where they definitively published all of their results. So yeah, it was about 8 years, and there were multiple projects that were part of the overall rate project, and quite a number of creationist researchers involved. In fact, they perhaps it just helped just to sort of tell people about who exactly was involved in this.
That was going to be my next question.
Right. Okay. So there are a couple of geologists, Dr. Stephen Austin and Dr. Andrew Snelling. So a soft rock and a hard rock geologist. There was a geophysicist, Dr. John Baumgardner. 3 physicists, Russ Humphreys, Gene Chafin, and Don DeYoung. And then the chairman of the group for ICR was Dr. Larry Vardaman, who's a meteorologist. So he kind of just chaired the group. And they involved a number of other people along the way, including a Hebrew scholar, Dr. Steve Boyd, who I think we interviewed on our podcast a while back.
Yep.
He did a project about the proper reading of the Hebrew text of Genesis chapter 1 that sort of came under the rate banner. But most of the projects were obviously focused on the science of radiometric dating.
Sure. Yeah, and that's where most of the money was spent, right? I mean, that's where doing all these experiments and collecting samples and paying for processing and everything else.
Yeah.
Now I gotta rewind just a second here, because you said something weird. Hard rock and soft rock. I've touched a lot of rocks in my day. I don't think I've ever found one that I would say was soft. Can you help us out with that? What is a soft rock?
Okay, it's just kind of shorthand, geological shorthand. Soft rocks refers to sedimentary rocks, and hard rocks are igneous and metamorphic rocks. So we tend to talk about these major divisions in the geological sciences.
So this is relatively speaking, the soft rocks.
Yes, relatively speaking,
relatively softer than the harder rocks. Okay.
Yeah, that's right. Yeah.
Okay.
The igneous and the metamorphic rocks are often crystalline rocks, and obviously the sedimentary rocks are usually made up of mineral grains that are cemented together. And so, yeah, we talk about soft rocks and hard rocks.
Excellent. Thanks for clearing that up. So that's quite a team. I mean, that covers quite a lot. I mean, from what Dr. Clausen told us, we learned about all the physics involved in the atoms. There's geological sampling that's done, and there's all the processing that goes into this. And as you said, they brought in Steve Boyd to help them work through some of the scriptural implications. What was the goal of this? Were they just trying to show that radiometric dating is bogus and we shouldn't believe it? Or what was, haven't we already done that by that point? What was going on here? I'm not sure I'm clear on what the objective was.
Yeah. Okay. So it wasn't a debunking project. It wasn't just about attacking radiometric dating. Although they did obviously look at, what are the assumptions that underlie the various radiometric dating methods and what might be some of the problems with those assumptions. But it was really a more positive attempt to try to understand what the radiometric data really mean within a young Earth context. So I think, going back to the early meetings that RATE had, they established some kind of guiding principles for their research. One of those guiding principles that was agreed upon early on was that the biblical record was basically a record of a young world, recent creation. You know, the rate researchers were all agreed on that the Earth had been created about 6,000 years ago, and there was a worldwide flood in the days of Noah. So that was a basic sort of guiding principle.
Sure.
But then they also had quite a bit of discussion about the exact approach that they would take in terms of the research. What would be the particular focus? And one of the things that I think came out of those early discussions, there was disagreement. People didn't always agree, but they kind of reached a consensus. And one of the things that they decided was that there was indeed a great deal of evidence that a large amount of radioactive decay had taken place in the Earth's past. And so that again became one of the sort of guiding principles of rate. We have this evidence of large amounts of nuclear decay, and we need to understand it within a young Earth context. So that was really what they set out to do.
That's different than just showing that it's wrong. They're trying to show, they're trying to understand what the evidence really means if it's not actually millions of years of history.
Yes, because I think, what can tend to happen in some of these discussions about radioactive dating is that people can cherry pick the data. So quite often, we can look at the overall trend. We can see that older rocks tend to give older radiometric ages and younger rocks give younger radiometric ages. And we can say, look, there's this fantastic trend. You get this nice sort of straight line on the graph. We can ignore perhaps or overlook some of the potential problems and pitfalls and some of the anomalies and the outliers and the things that don't quite seem to be as expected. Mm-hmm. On the other hand, I think what some creationists have sometimes tended to do is to focus on the anomalies and the outliers and not account for the overall trend in the data. And I think what the rate group were wanting to do was to be able to explain all of the data. They wanted to be able to explain the overall trend, but they also wanted to explain the anomalies as well. And so that was really what they set out to do.
Yeah, that makes sense. So when you say older rocks and younger rocks, you're talking about, I'm going to guess here, you're talking about, say you have like a single place where there's lots of layers and you start with the bottom layer and you date that one. That's the older layer because basically in geology and frankly any other stacking pancakes, you have to put the bottom cake down first and then put other cakes on top of that. You can't start with the top. So you can, if you have a column like that, you can sort of guess, well, this guy down here must be the older one and these up here must be and it's not really a guess. You kind of know that this must be how it is, right? I mean, that's what you're talking about.
Yeah, you can essentially work out the sequence, the
right.
order in which various geological events happened independently of the radiometric data. And then you find that the radiometric dates broadly fit that pattern.
Okay.
Things that happened first give older dates, and things that happened later give younger dates.
Well, that's pretty important. I mean, if you're telling me that happens a lot, then that seems like the thing as a scientist we would want to explain, right? I mean, that scientists want to explain the main parts of the data, so that would be the thing we would want to focus on, and that's what rate is doing, right? I mean, that's the idea. Okay, good.
Yeah.
Okay, I'm following along. This is good. All right, so we've got these scientists. They are physicists. They are geologists. I know Andrew has done a lot of work. Andrew Snelling, not just Andrew, but Andrew Snelling has done a lot of work on radiometric dating. So these were people who were qualified and able to do this sort of work. Okay, so they got together for many years, raised and spent $1 million, which was a lot of money. So practically speaking, the outcome of the project, I remember at the beginning they published a couple of books, like a 2-volume set. Is that right? And then at the end they published another 2-volume set.
No, it was a single volume.
Okay, it was a single volume at
the beginning. So this is the first volume. This came out in 2000.
All right.
So quite early on in the project. Remember, they had their first meeting in 97. This book came out in 2000.
Okay.
And this book, it's about 700 pages, so it's a substantial volume.
Yeah.
And this really sets out the state of the art. It kind of reviews the literature on radioisotope dating. It sets out what some of the challenges are for the creationist viewpoint, and it sets out some potential avenues of research that they were intending to undertake. So that came out in 2000. What came out in 2005 was another volume. It's even bigger. This is over 800 pages, and this is the results book. Okay. So this was 2005, and over the course of the project, they published a number of peer-reviewed articles, peer-reviewed papers about the work. But the definitive publication of their results was in this second volume that came out in 2005. There was another book, which was this one, right? This paperback, and this could be very helpful to some of our listeners and viewers, because this was a kind of layperson's summary of the RATE project. So this came out again at the end of the RATE project when it was concluded. And it summarizes for, the average person, the results of the RATE research. So if you're not ready to tackle this massive, 800-page technical volume, that's the book to read.
That's the book to read. All right. Must be. I see the second book there is marked volume 2. That's probably where I got my wires crossed and started thinking there were 2-volume sets here. But okay. Yeah. Okay, so big books, lots of research, lots of people, lots of money. What exactly did they discover? I mean, what was... and I should preface this. Remember, all of our listeners and viewers, this is a series, right? We're going to be... continuing talking about more issues in radiometric dating. We are not going to just do one and done and go on to something else. And it will be intermittent. I don't know when the next one is. I don't know what the subject will be right now, but we will do more. So as we go through the results of RATE, and you're thinking, oh, this is too much, I can't understand it all. I don't either, right? So we're gonna have future episodes where we talk in depth about a lot of these things. We will probably get some RATE people who are involved in the project to be on the show to help us understand what happened. But this is our overview episode. So Paul, why don't you walk us through some of the results that came out of the project?
Well, I want to go back just briefly I want to go back to one of those guiding principles that I talked about that underpinned RATE, because I think that might be something that a lot of our viewers want to hear about, which is this idea that there has been a lot of radioactive decay in the Earth's past, because that was one of the things that the RATE researchers reached a consensus on. And people may be wondering, well, how do we know? How do we know that there's been all of this radioactive decay? And in fact, there are multiple lines of evidence. And again, you can read that about that evidence in the technical RATE volumes. But let me just kind of briefly summarize some of that evidence. One of the first things is that when we look inside rock minerals, we find that there are the parent isotopes, the radioactive parent isotopes, along with the daughter isotopes that were produced by the radioactive decay of the parents. And there they are in the rock minerals, side by side with one another. So, for example, uranium-238, when it decays, it goes through a series of steps. It's called a decay chain. I think there are about 15 different isotopes involved in the decay chain of uranium-238 to lead-206. And inside rock minerals, we find not only the uranium-238, but we find the daughter products. And we find them in the proportions that we would expect if they'd been produced by nuclear decay. So that's a pretty powerful evidence. So we know that decay has happened within those rock minerals since those minerals formed in the rock.
Okay. Let me ask you this question then. So U-238 goes through some sort of radioactive decay, and you're talking about a chain here. So the product of that decay is also radioactive. Is that the idea?
Yes.
Okay.
Until it reaches a stable daughter like lead-206.
So there's all these
which isn't
steps.
radioactive.
In this chain, there are these steps, and each product is also radioactive until it finally lands on lead-206, which is stable and does not decay any further. Okay.
Yeah.
So are there other lead forms, right? So we talked about isotopes. We talked about elements that have the same number of protons. So they're the same element, but different number of neutrons, so that they actually weigh slightly different. Are there other leads, right?
Yeah.
So we can tell that this kind of lead comes from this kind of uranium. Is that just...
Yeah.
Yeah.
And what we find are all of those decay products of uranium-238. Okay. So we find all of them in situ in the rock minerals and in the amounts that you would expect if they'd been produced by the nuclear decay of uranium-238. So that's pretty compelling. And the reason this is important is because I think in the past, what some creationists have tried to say is, well, we can account for the isotope characteristics of rocks maybe by inheritance, that, when these rocks are often formed from a magma, they're igneous rocks or volcanic rocks. And maybe those isotopes were just brought up with the magma when the rock was formed. So in effect, they had a kind of built-in inherited age. Right. Now we know that inheritance happens. There are occasions where, you know that an age is actually an inherited age from a deep source. Mm-hmm. But when you find within rock crystals, you find all the products of the uranium-238 decay chain in the right proportions in those rock minerals, then clearly that's the product of decay that happened since those minerals formed. So those are not isotope ratios that have just been inherited. They're the product of decay in situ in the rocks. So that's quite important. But that's only one piece of evidence, because there are others as well. Okay. I mean, a couple of other pieces of evidence concern actual physical defects in the rocks that are produced by the products of decay. So, for example, there are these things called radiohalos. Now, think about uranium-238 again.
Okay.
When uranium-238 decays, it decays by something called alpha decay. It gives off alpha particles. Alpha particles are effectively 2 protons plus 2 neutrons. Mm-hmm. That's an alpha particle. These alpha particles, as they're emitted from the decaying nucleus, damage the surrounding mineral lattice, around the decaying nuclei, and they discolor the mineral, and they form a series of concentric halos of discoloration, damage. And again, you find these concentric spheres of damage, and those spheres have distinctive diameters, and you can relate those to particular isotopes in the decay chain that have produced that particular diameter halo. So what we have, in other words, is direct evidence of alpha emission, alpha particles being emitted during decay. And we know that we must have enough of those alpha particles being emitted to produce these mature halos. And that amounts to maybe hundreds of millions of years worth of nuclear decay at present day rates.
Okay.
So again, we have direct physical evidence of damage, if you like, caused by the decay process.
So the halos, let me see if I can understand this here. So I imagine I have some uranium-238, and I have and I've seen this before. So I've seen these crystals, and I've seen the little little smidge of radioactive stuff in the middle that has been decaying. And that consists of many, many atoms of uranium 238, right? So we're not talking about just one atom.
Yeah.
And
Just one. No.
every time one of those breaks down, it shoots off an alpha particle. But it's going to shoot it off in random directions, in every conceivable direction, which then leaves that distinctive ring structure in the rock as and it's determined, as you say, by the energy of the particle, right? How energetic it is as it's decaying, shoots it off, and it's basically like shooting a cannon. And if you put in a lot of powder, it'll go a long way. And if you put in a little powder, it goes a short way. But it's going in any direction it can. And over the time, then it's going to shoot in every direction, which gives you this circular stuff on the rock that you can see under a microscope.
Yeah, that's exactly it.
Okay, good. And that then tells us, when we see those marks with the gunk in the middle that is the radioactive decaying stuff, that tells us that must have been produced by radioactive decay in some way.
Yeah.
Okay.
And a lot of decay.
Because they're everywhere.
Lots of these decaying nuclei.
Yeah.
Yeah.
Okay,
yeah.
cool.
And they're everywhere.
I'm following.
And there are there's another kind of damage, which is a bit different, called a fission track. So what sometimes happens is that an unstable nucleus will just fission. It will split into two, effectively sort of equal halves, roughly half the mass of the parent nucleus. And these halves will just rip apart through the surrounding mineral. And they leave a track as they separate from one another. A line of damage. And these fission tracks, you can see them in the minerals under the microscope, and you can do fission track counts. So you can count the number of these things, and you can therefore estimate how much nuclear decay has happened within that mineral. And again, the numbers of these fission tracks in many samples indicate millions of years worth of nuclear decay at present day rates.
Okay. So assuming everything is going along like it's always has, as we've observed, that would be millions of years of decay.
Yes. Yeah.
Provided our assumption is correct.
Yeah.
I'm kind of hinting at where we're going with this here.
Yeah.
Okay.
And one last piece of evidence that also sort of points to large amounts of decay is that in nature, we have an absence of short-lived radioactive isotopes. Of all of the radioactive isotopes that are not currently being produced, because some radioactive isotopes are being produced by processes in the natural world. Okay. But of all those that are not being currently produced by natural processes, only the isotopes with half-lives greater than about 80 million years or so are found in nature. So the shorter-lived isotopes are missing. And how do we explain that? Well, one way to explain it would be to say that a large amount of nuclear decay has happened, that the Earth, has been around for long enough that those shorter-lived radioactive isotopes have all long since decayed away. And again, that implies millions of years worth of decay, if we assume that rates have always been the same as we observe them today.
I'm kind of puzzled by that. 80 million year half-life. Is that what you're talking about? 80 million year half-life?
Yes. Yeah.
And there's this weird absence of those things with half-lives less than that. And we're talking about things that have been discovered in like nuclear particle colliders and stuff like that, where you've been able to produce these weird things that don't occur in nature and observe how rapidly.
Yeah, we're not. Yeah, we're only talking here about ones that that can't be produced
Right.
naturally,
Right.
or ones that we, not ones that we're producing in colliders or whatever. These are just ones
right.
that occur in nature, but they're not being currently produced in the natural environment, but they are effectively missing. So we can produce them, right? We can produce them artificially, right, in colliders, but they're missing in the natural environment.
I'm a little baffled by this, because if you would think something with a half-life of, say, 60 million years, why would there not be traces of those things? I mean, why? That seems so weird. Even from a conventional standpoint, I think that's kind of weird. Maybe I don't understand.
Maybe this is another area where we need to talk to one of our experts.
Definitely.
And get some more insight.
We're gonna go back over this episode as we make up the show notes, and we're gonna just make all the notes about who we need to talk to, because we don't really understand this part and we don't understand that part. Yeah. Good stuff. All right.
But but that's what I'm told, that the absence of these short-lived nuclides, the short-lived isotopes, is consistent with millions of years worth of radioactive decay.
Yeah, that makes sense. I mean, it makes sense that there would be a dearth of those kinds of things. It just strikes me 80 million years was not what I was expecting you to say. I was expecting you to say 5 million years or 10 million years. And I would think, oh yeah, well, that makes sense. 80 million years that's a long half-life. Anyway, let's not belabor that point. Let's just chalk that one up to, let's ask an expert when we get him on here. Okay. So we've got, evidences of radioactive decay. We've got the elements or the isotopes in the decay chain occur in the expected ratios. We've got damage marks in the form of the radiohalos and the fission tracks, which blows my mind. An atom just decides, I don't want to be an atom anymore. I'm just going to bust into two. And I thought radioactive decay was weird, but that's even weirder. Okay, so that's that. And then there's these absence of short half-life. So those are 4 things there that sort of say that there really has been radioactive decay. Is there anything else on that list that we're missing?
No, I think those are the main evidences that persuaded the rate team that there had to have been a lot of nuclear decay in the Earth's past, and that had to be accounted for.
Okay.
And given the biblical constraints that the Earth is only about 6,000 years old, we have to account for all of that evidence of decay in a short time frame.
Yep. Which then leads us to conclude, even I can conclude this, then that must have been a lot of radioactive decay in a very the rate, to use a double entendre, the rate of decay must have been very accelerated in the past. Must have been a lot faster than it is today.
So
that's where they're going, right?
That was the conclusion that they drew.
Okay.
That it was a logical inference that if you have a short time frame and you have an awful lot of radioactive decay, there had to have been an acceleration of radioactive decay rates in the Earth's past.
Okay.
And they proposed that perhaps there were a couple of episodes of accelerated nuclear decay, one during Creation Week and one during the flood, during Noah's flood. So that was essentially sort of a kind of headline conclusion from the rate work. Now that's pretty radical.
It is kind of radical, yeah.
We are used to thinking in terms of constant half-lives, constant decay rates, and to suggest that radioactive decay rates had been accelerated by, a billionfold in the Earth's history, that is a really radical conclusion, and it requires some new understanding of physics and physical processes, isn't it? And in fact, that was really the focus of Gene Chaffin's work on the rate project, because the work that he did was sort of focused on theoretical mechanisms of accelerated radioactive decay. So he was thinking about what physical constants, what physical parameters might have been different to allow for accelerated nuclear decay to happen.
So when you said this was radical, yeah, it is definitely physically radical. I was thinking it was radical for a creationist to say, honestly. I grew up a long time ago. And when I was growing up, I was reading books that were written by sort of the first generation of people studying radiometric dating. I mean, radiometric dating has not been around very long at all. We have not even been a century yet that we've been doing radiometric dating. So as I'm reading these early creationist books, I'm reading things like, well, if you date this fresh lava flow, it's 5 million years old. So clearly radiometric dating is bogus. And that's kind of the message that I remember taking to college with me, was that, it just doesn't work. They say it works, but it doesn't really work. And now you're telling me, there is radioactive decay, that it isn't just all bogus, that there has been this decay. That does sound kind of radical. And I guess now, years after RATE's been done, it sounds less radical to the new generation of creationists. But for me growing up, that was a kind of a big deal to come to this conclusion that no, there has been radioactive decay. Does that sound familiar to you, Paul? Did you have a similar sort of experience too? Yeah.
Yeah, I think that's absolutely right. I think for a lot of people, this was kind of a new revelation, wasn't it? That actually the evidence for large amounts of nuclear decay in the Earth's past was pretty robust, and it needed to be accounted for. Because I think in the past, there'd been all kinds of other ways to sort of try to approach the question of radiometric dating, but I think usually people had assumed that there hadn't been a lot of nuclear decay in the Earth's past, that isotope ratios in rocks perhaps were just isotope characteristics that have been inherited from the time of creation or something of that kind.
Yeah.
Whereas there actually does seem to be some kind of history involved here.
Yeah. Okay. So we have sort of one of the projects that came through the RATE project was, as you mentioned, Steve Boyd's biblical studies, which affirmed the basic narrative character of Genesis 1. And by inference, then, that it's telling us something about the real history of the world. And therefore the Earth is not really millions of years old. So we conclude then that there must have been accelerated decay, which is, as you mentioned, a radical physical idea. And some people might even say it's crazy, but okay. So is there evidence from RATE that that's really what happened? Or is this just wishful thinking on their part?
Well, I think this is where it gets kind of wild, because I think if it was just a kind of ad hoc idea that was just sort of pulled out of the air to try to explain large amounts of decay, that would be one thing. But what the RATE group did was they did a number of projects, some of which seemed to actually provide evidence that there had been some kind of episode of accelerated decay in the Earth's past. So let me tell you about one of them.
Okay.
So one of these projects concerned helium in the rocks of the Earth's crust. So you remember that I said that uranium 238, when it decays, it gives off alpha particles. Alpha particles are 2 protons and 2 neutrons.
Yes.
Well, in
that's
effect,
helium, right?
That's a helium nucleus.
Yeah, that's a helium nucleus.
2 protons plus 2 neutrons. So, and for every uranium 238 atom that decays, you get 8 helium nuclei
produced.
And these helium nuclei sort of grab electrons from their surroundings, and they become helium atoms. And the helium atoms can then, it's helium's a gas, right? So helium can then diffuse out of the minerals in which it's produced.
Okay.
So
and then helium, the other thing I know about helium is that it's lighter than air and it's just going to go float away, right? I mean, that's basically what's going to happen to it.
Yes. Okay. Yeah. It's going to escape. It's going to escape pretty readily.
Yeah.
Now, the rate group were aware of a place in New Mexico where they had done, I think they were drilling into these rocks for some kind of geothermal project. These rocks in New Mexico were granitic rocks. They had a radiometric age of 1.5 billion years.
Okay.
And one of the interesting things that came out of this geothermal project was that they'd measured the amounts of helium in these crustal rocks, and there was a lot of helium in these rocks, consistent with a large amount of decay, consistent with 1.5 billion years of nuclear decay. I think up to 58% of the helium that was predicted was actually there in these crustal rocks.
Okay. So this is the helium produced as they've decayed over 1.5 billion years.
Yeah. Okay. And the helium that you'd expect is right there. It's in the rocks.
It's still in the rock.
It's in the zircon crystals in the rocks. Zirconium silicate crystals, within these granitic rocks contain, large amounts of helium.
Okay.
So what the rate group decided to do was to commission some experiments on helium diffusion from zircon crystals. So they collected samples of these rocks and they sent them off to a laboratory that could do these kinds of high precision measurements of helium diffusion through the zircons. And what they found was that the rates of helium diffusion were so high that these zircon crystals simply couldn't have retained the amounts of helium that were measured in them for more than a few thousand years.
Oh, 1,000 years.
Yeah.
Okay.
So the time scale of helium diffusion was in only thousands of years. Now that's really, really interesting. It obviously varies a bit depending on the temperature, of the rocks.
Yeah. Yeah.
So, you measure it over a range of temperatures, but they've basically found that given the geological history of this particular site, you wouldn't expect the helium to be retained for more than about 6,000 years. Now, can you see, a potential problem here?
I see the problem. I mean, if this is, and let me see if I can explain it and you tell me if I got this right. So we've got a rock that formed by radiometric dating 1.5 billion years ago. And so the uranium or whatever that started in that rock and has been there for 1.5 billion years has been producing little heliums the whole time.
Mm-hmm.
And if helium goes away in thousands of years, then those rocks, that helium should have flown the coop and long gone. There should be basically no helium left in those rocks.
That's exactly it.
It should be unmeasurable, I would think. Something like that if it goes in thousands of years. So why do these rocks still have so much helium in them?
Yeah. So interesting question. Why do they still have such a large amount of helium?
Right.
It kind of looks as though there was a huge amount of radioactive decay that generated a very large amount of helium, but that episode of nuclear decay must have been within the last few thousand years to account for the fact that the helium is still there.
Right.
So, that seems consistent with the hypothesis of accelerated nuclear decay rates.
Mm-hmm.
Large amounts of nuclear decay, but within the recent past.
Right. Yeah. I can follow that. That makes sense.
You can follow.
Yeah.
So that was one piece of evidence. Got a couple more for you.
Okay.
Another one concerns the radio halos. You know, we talked about radio halos before. These spherical areas of damage, discoloration caused by alpha particles, being emitted from decaying nuclei. Uranium-238 radio halos are made up, I think, of, if I remember rightly, 8 concentric spheres. And each of those spheres represents a particular isotope in the decay chain of uranium-238. It's firing out alpha particles. And 3 of those concentric spheres in a uranium radio halo are produced by very short-lived isotopes of polonium, the element polonium.
Okay.
There's polonium-210, polonium-214, and polonium-218. And these isotopes are very short-lived. They have very short half-lives. So polonium-210 has a half-life of 138 days. Polonium-218 has a half-life of just over 3 minutes.
Oh.
And
so that goes literally that fast.
Yeah, goes like that. And polonium-214 has a half-life measured in fractions of a second.
Oh,
so these are these are fast decayers.
Yeah. Okay.
Now, there's been a long-standing mystery, which is that in granitic rocks around the world, we often find polonium radio halos that are so-called parentless polonium halos. In other words, they're isolated and are not part of a uranium-238 halo. Their parent uranium-238 is kind of missing. So you get these polonium radio halos that are isolated, not part of a uranium radio halo. So how did they form? What the rate group proposed is that at the time these rocks were forming, uranium-238 is decaying and it's producing the various isotopes in the decay chain, including the polonium isotopes.
Mm-hmm.
And as these polonium isotopes are forming, they are being transported by hot fluids, because these rocks, as they cool, their hot fluids are circulating through these rocks, and the hot fluids are able to transport the polonium isotopes away from the parent uranium, and they get concentrated into new sites, into new decay sites, new radio centers, where they continue to decay and then produce a halo of their own that is separate from the uranium halo. Now, this also has interesting timescale implications, and implications for accelerated nuclear decay, because in order to form these polonium radio halos, you need an abundant supply of polonium, and that means lots of decay of uranium. Okay? So you've got to have millions of years worth of uranium decay to supply the polonium to form the polonium radio halos. But the polonium radio halos have a fleeting existence because those isotopes are so short-lived.
Sure.
And you also have a very narrow window of time when they can form, because the radio halos can't form in the rocks until the rocks have cooled to at least 150 degrees, because above that they just get thermally erased. You can't actually retain the radio halos; they don't form. Okay. So you've got to get to temperatures below 150 degrees, the thermal erasure temperature, for the halos to form, and at the same time, you've got to still have plenty of hot fluids flushing through the rocks to supply the polonium. And as the temperatures fall, the convective system that's driving the hot fluids also begins to shut down. So you actually have a very narrow window of time when you can produce these things. And what the rate group argued is that when you put all of that data together, it looks as if millions of years worth of uranium decay must have happened within a time window that is measured in perhaps days. So again, they argued that here we have some evidence. These parentless polonium radiohalos are evidence of accelerated nuclear decay.
Okay. Let me see if I can talk this back to you, because this seems really important. I want to make sure we got this. So what they're envisioning happening is that you have so you have a bit of uranium that has been decaying and producing polonium. So now there's a bit of polonium. And that polonium then gets moved away. So there was at some time all the uranium halos around that bit of stuff, right? Around that bit of polonium. But then water came in and moved that polonium to a new location. Is that right?
Yes.
And then it starts decaying again, and it generates in that new spot all the polonium halos. But it can't happen. It can't happen slowly, because polonium doesn't last long enough for it to happen.
Yeah.
It has to be quick, both producing the polonium and moving the polonium, and then the polonium can decay again. Okay.
Well, it's decay. I guess it's decaying the whole time. But
sure. But it
only forms a halo when it gets. It only forms a halo when it gets
right.
concentrated in a particular radio center.
There's a little spherical smudge of it somewhere that is lodged in some spot in the crystal. And when we're talking about crystals here, the ones that I remember seeing, these were mica. Is that right? Mica. So they had flat flakes of it. So there's all of these layers in the crystal structure, and there's these microscopic tiny space between them where the water could move stuff, really tiny stuff. Okay. Yeah. Because I can imagine people going, how is water going through rock? Water does go through rock.
Yeah.
There are these small channels and openings, rock. And if you've ever, looked at a wet rock, rocks can get wet and they can stay wet because the water has seeped into the rock. So that's what's going on here. So it has to move quickly in order for for there to be any polonium halos at all, because otherwise the polonium would decay quickly, probably right there in the uranium center. You would never see a polonium halo by itself because it goes so fast. Okay.
Well, you see polonium halos as part of a uranium halo.
Yes, exactly.
You do see those, but you also see them as isolated parentless halos, and they're the ones that are a real mystery.
Yeah, that's the mystery, because that shouldn't happen.
Yeah.
Okay.
They've got to form quickly. They've got to form quickly.
Yeah.
But you've got to have millions of years worth of uranium decay to supply the polonium,
to produce the polonium,
for the halo to form. But the halo's got to form quickly. So here's the argument that this is accelerated. There's
something wrong with those two things. You can't have them both. So something must be funny with the way the uranium is decaying, the rate at which uranium decays. All right. Any final things to talk about from our little rate overview here? Anything you want?
Well, just one other brief thing that again, touches on this accelerated decay idea. We talked in earlier episodes about the idea of concordance, the agreement between different radiometric methods. So if you date the same samples, you would expect, whether you're using samarium neodymium or whether you're using uranium lead or whether you're using rubidium strontium, you'd expect the same samples are going to give roughly the same ages.
Sure.
And often that's the case.
Okay.
And, we talked to Ben Clausen about that.
Mm-hmm.
What the rate group did was something interesting. They selected a number of rock units where they dated the rocks by multiple methods. So typically 4 different radiometric dating methods.
Okay.
And what they found is that in many cases there was strong discordance. In other words, strong disagreement between the results from different radiometric dating systems on the same rock or mineral samples.
Okay.
And these were not small percentage differences often. They were often quite large differences. Now, what was even more interesting than the simple fact of discordance was that there was a pattern to the discordances. So isotopes that had longer half-lives tended to give older ages than isotopes with shorter half-lives. And isotopes that decayed by alpha decay tended to give older ages than isotopes that decayed by beta decay. So what this meant, in effect, was that there was a kind of pecking order of dates.
Yeah.
So on the same sample, samarium neodymium would tend to give older ages than uranium lead. Uranium lead would tend to give older ages than rubidium strontium. And rubidium strontium would tend to give older ages than potassium argon on the same samples.
Okay.
And the question we have to ask is why?
Yeah.
If radiometric dating is giving us an indication of the true age of these rocks, why are the different dating systems giving us different ages? And it can't just be random error, because otherwise you wouldn't expect a pattern, right?
Exactly.
You would just expect that sometimes samarium neodymium is going to be older,
Yep.
sometimes it's going to be younger.
Doesn't matter.
But actually there was a more consistent pattern.
Yeah.
And that may also be a clue to something else that's going on.
Yeah.
It may be that during the episode of accelerated decay, isotopes that had longer half-lives and that decayed by alpha decay were accelerated to a greater extent than those with shorter half-lives or that decayed by beta decay.
Right.
And that would explain the pattern. So again, this systematic discordance might be a clue that something quite wild is happening.
And I think that's really important because, when you do radiometric dating on a single rock and you find, 4 different dates that differ by more than just the random error you would expect, the easy conclusion is, well, this doesn't work. Who knows how old this rock is, right? And you just sort of shrug your shoulders and say, it's all made up. These scientists are just making it up. But when you realize that the error is always in a certain direction, that becomes a pattern. And that pattern is exactly what scientists love to explain, right? That's exactly what we're looking for.
Yeah.
Because if it was, as you say, if it was just random, which is what you'd expect if it was just totally meaningless, then it wouldn't, it would be random and there wouldn't be anything to explain. But when we have something where you can always say, this method is always going to give you a date that's slightly older than this method over here, now that's something worth exploring and trying to explain. That's a little more than just random error.
Yeah.
So that strikes me as rather important. Okay, well, we're now at the end of our episode. I would love to go on and talk about more things. But time to wrap up. And I want to encourage everyone listening. If you're thinking, yeah, but rate is bogus and we have reasons why, we're going to talk about that in some future episodes. And if you're thinking, I don't understand anything about that you just said in the past hour, that's cool. We're going to come back and try to explain things even better with some experts who can help us understand and answer all of our technical questions. So remember, this is a series, and we'll be back to these issues in the future. Meanwhile, don't forget to leave that like on the video, give us a follow or a subscription, depending on what platform you're on. If you're on YouTube, you can click the bell to receive a little buzz on your phone every time we post something new. We're always pretty much every fortnight, we're going to release a new episode. You can find us also on social media, Facebook and Instagram and Twitter, and also the sponsoring organizations. Paul, tell us about Biblical Creation Trust.
Yes, Biblical Creation Trust is one of the sponsoring organizations, and you can check us out at our website, biblicalcreationtrust.org. We're also active on social media. You can find us on Facebook. And if you visit our website, there's a link on the homepage, a donate button, and that will take you to a giving page where there are all of the information that you need, all of the information there about how to give by PayPal or direct bank transfer or whatever you want to do. And we really do appreciate your support because it helps us to keep all of this great content coming.
Great. And in the United States, this podcast is sponsored by Core Academy of Science, which you can find at coresci.org. If you go to coresci.org/connect, you can find links to all of our important content that we want you to know about, including our social media and ways that you can financially support Core Academy here in the U.S. If you would like to know more about the podcast, visit coresci.org/podcast. That's coresci.org/podcast. And if you'd like to interact with us, you can do it on Facebook, Instagram, Twitter. You can also send us an email, podcast@coresci.org. If you've got questions you want answered, we'll consider those for future episodes, or maybe we'll just write you back with the best answer we can come up with. And we do want to thank you again, everyone, for listening and watching this episode, and we'll see you back here in 2 weeks' time. See you then.
See you in a fortnight. Bye-bye.
Thanks for listening to this week's episode of Let's Talk Creation. If you have questions, send them to podcast@coresci.org. That's podcast@coresci.org. And be sure to let your friends know about Let's Talk Creation. And check us out on social media. Thank you.